What's up, Chem peeps? Who's ready for one more free response? I know I am. I live for this. A solution of 0.100 molar HCl and a solution of 0.100 molar NaOH are prepared. A 40.0 milliliter sample of one of the solutions is added to a beaker and then titrated with the other solution. A pH electrode is used to obtain the data that are plotted in the titration curve shown above. Boom! Part A. Identify the solution that was initially added to the beaker. Explain your reasoning. The solution in the beaker was the 0.100 molar HCl because the initial pH was 1. This is the pH of a 0.100 molar HCl solution. Boom. Done. Check out our titration curve. Initially, we start down here in the acidic range. Makes sense that HCl was in the beaker to start. Boom. Part B. On the titration curve above, circle the point that corresponds to the equivalence point. Oh man, I shouldn't have circled that earlier one. Alright, for your equivalence point, you're looking for that sharp change in pH right here. Additionally, strong acid, strong base, our equivalence point is going to occur at pH 7. Circled. Part C. At the equivalence point, how many moles of titrant have been added? So here's a fun vocabulary word. Recall that the titrant is what is in your burette. We know the concentration and we carefully measure the volume of that titrant. Analyte is what's in your beaker. That's what you're analyzing. So as we think about part A, we decided that the HCl was in the beaker, which means that the burette must be filled with the sodium hydroxide, and therefore is our titrant. As we look at the information provided, 0.100 molar sodium hydroxide is used, and in order to reach the equivalence point, which we just circled in part B, it required 40 milliliters. So I'm going to use my molarity equation, recognize the concentration, looking for moles, my volume, 40 mils. Calculator. 0.100 answer. X equals 0.00400 moles NaOH. Boom. Moles of titrant. Moving along to part D. The same titration is to be performed again, this time using an indicator. No pH probes allowed. Use the information in the table below to select the best indicator for the titration. Explain your choice. Alright, to answer this question, you want to think about what is the pH at the equivalence point. And we've decided that it's pH of 7. And we want to choose an indicator that has a pKa that's closest to that pH. As I look at my list, it explicitly tells us the pH range of the color change. If we choose methyl violet, it's going to change color between pH 0 and 1.6. It's going to be way down here. It's going to definitely miss our equivalence point. Check out methyl red. It changes in a pH range between 4 and 6. So I go back up here and think about my titration. Notice that we'll see that color change fairly close to the pH of our equivalence point. Our last option, alizarin yellow, has a pH range of color change between 10 and 12. If I were to choose that, we would have already passed our equivalence point when we see the color change. So, methyl red would be the best indicator because its color change will occur closest to the equivalence point of the titration. Boom, done. Part E. What is the difference between the equivalence point of a titration and the end point of a titration? Oh, so much great vocabulary in this free response. The equivalence point in a titration occurs when the number of moles of titrant is exactly sufficient to react with the number of moles of analyte. Boom. So in this example, the ratio between our titrant, NaOH, and the analyte, HCl, is 1 to 1. So if I had 1 mole of HCl in a beaker, I would need to add 1 mole of sodium hydroxide to reach my equivalence point. Not needed for this answer. Just an example. The end point in a titration is the point in a titration at which the indicator undergoes its color change. Boom. So two very important terms for titrations, often confused. Equivalence point is when you reach that stoichiometric ratio between your reactants. Endpoint is when you see that color change. Don't mix them up. Finally, part F. On the grid below, sketch the titration curve that would result if the solution in the beaker was 40 mils of 0.100 sodium hydroxide and the solution in the burette was 0.100 molar acetic acid. The equation representing the reaction in the titration is shown below. Boom! The Ka of acetic acid is 1.8 times 10 to the minus 5. Okay, now I know it's tempting to come up with a bunch of different plots. However, in the essence of time, I think it's probably best to come up with an initial point, an equivalence point, and a final point. And then again, just sketch in the rest. So let's think about what we have initially. 40 mils of a 0.100 molar sodium hydroxide solution. If that's what we're starting with initially in our beaker, it's just a strong base. And if the concentration of my sodium hydroxide is 0.100 molar, then I know the initial concentration of my hydroxide ion is 0.100 molar. But be careful, because it's a hydroxide ion, we would solve for the pOH, which is equal to the negative log of the hydroxide ion concentration. I plug in my value of 0.100 molar. I don't even calculate it here. pOH equals 1. But my graph has a plot of pH against volume of titrant. So to determine pH, keep in mind this handy dandy relationship. Boom. So my initial pH, my starting pH, is going to be a pH of 13. Makes sense? Strong base. Boom. Plotted. Next, let's determine the pH at the equivalence point. Remember, at the equivalence point, think about how we just defined it in part E. We have the exact stoichiometric ratio of sodium hydroxide and acetic acid. These have all been completely used up. And so we formed our salt and water. Now, at the equivalence point, we're concerned about the salt and how the salt contributes to the pH. Because this salt comes from a strong base and a weak acid, the salt is going to be a basic salt. In other words, the pH at our equivalence point is going to be slightly basic. Now, the ion of the salt that's going to contribute to the basic pH of our solution is going to be the acetate ion. And its reaction with water is as follows. Boom. I need to know what the hydroxide ion concentration is so I can determine the pOH, and from there determine the pH. But the acetate ion is a weak base. So to determine the concentration of hydroxide ion, I need to use an ice table. Boom. To drop my water. Let's think about what the concentration of the acetate ion is going to be in solution at the equivalence point, and use earlier parts of the problem to help you out. We've got 40 mils of a 0.1 molar sodium hydroxide solution. Take a look at our calculator. We already did a calculation to determine the number of moles that is. That's 0.004 moles of sodium hydroxide. And so if I have 0.004 moles of sodium hydroxide, I'm going to need 0.004 moles of acetic acid to completely neutralize it, and I'll make 0.004 moles of sodium acetate. And because I have equal concentrations of sodium hydroxide and acetic acid, I must have added equal volumes to reach my equivalence point, which means that this 0.004 moles of sodium acetate is in 80 milliliters. 0.004 divided by 0.080. So my concentration of acetate ion at the equivalence point is 0.0500 molar. 0 and 0 minus x plus x plus x. At equilibrium then, 0.0500 x and x. Be careful. This is the acetate ion. It's acting as a weak base, so I need to use a Kb expression. Boom. I'm given the Ka for acetic acid, so to determine the Kb of the acetate ion, calculator time. Parentheses 1.0 second E negative 14 close divided by new parentheses 1.8 second E negative 5 close parentheses answer. 5.6 times 10 to the minus 10 equals x squared over 0.0500. I made the x-small approximation in my head. Totally fine because we're just coming up with a sketch. So let's solve for x. Multiply 0.05 answer second square root second answer. So our hydroxide ion concentration 5.3 times 10 to the minus 6 molar. pOH equals negative log hydroxide ion concentration. We just solved for the hydroxide ion concentration. Calculator time. Negative log second answer. pOH equals 5.28. Again, keep in mind this is a pH versus volume of titrant added graph, so remember this important relationship. Plug in your pOH and solve. 14 minus second answer. pH equals 8.72. Boom. Let's plot it. Beautiful. Right, and then finally, after the equivalence point, realize we've got all of that conjugate base that we formed in the neutralization, and we're continuing to add weak acid, acetic acid. Anytime I've got weak base and conjugate acid, you guessed it, buffer. Here's the equation to represent my buffer system. In order to determine hydronium ion concentration, for a buffer system, we're going to use this equation. Now, I know my Ka, and I know from the calculation that I just did that at the equivalence point, I generated 0.0040 moles of my conjugate base. If I plot the point here at 80 mils, I've added another 40 mils of my 0.1 molar acetic acid. And as we recall, 40 mils of a 0.1 molar solution has 0.000400 moles. So after 80 mils, my hydronium ion concentration is essentially equal to my Ka. Boom. To determine pH, we're just going to take the negative log of the hydronium ion concentration, which is 1.8 times 10 to the minus 5. Calculator. Negative log 1.8 second E negative 5. Close parentheses, answer. 4.74. Boom. Finally, let's just sketch in our titration curve. Let's come up with a general shape here. Boom. Again, you're just sketching it in. Not necessary to come up with all the individual points along the way. We are done.